Hello, if this is working. Uh, yes. Okay, so welcome back, everyone. We've got a lot of nice talks about massive stars for the rest of the afternoon, starting with Varsha Ramachandran from Heidelberg. We'll be talking about UV insights on massive stars. So Varsha, I think you can just go ahead whenever you're ready.
We can hear you, yes.
We can't hear you super well. We'll see if we can get the audio fixed in the room. It's just very quiet. Um, I think that, uh, yeah, this is fine now, I think. Yeah, I think this is better. Go ahead. If you can hear us, you can start. Otherwise, I'll message or someone online maybe. Okay, thanks a lot, Varsha. Can you hear us? Um, hey, can you hear us, Varsha? maybe. In the meantime, do we have any questions? I can be handing the microphone out. Any questions online or in the room? We have one from Yorick. If Varsha can hear you through the microphone.
Can you hear me, Varsha? Okay. I was wondering about the CNO abundances, in particular nitrogen. How much more accurate do we get nitrogen abundances in massive stars if we also have the ultraviolet? So not just the optical, but also the ultraviolet. Thanks.
Okay, we have time for another question if anybody has anything else. Right. Otherwise, I think we can thank Varsha again. And the next speaker is Joachim. Yep.
Hello, can you understand me? This is the right one. Should be B.
This is the right folder, right?
No, this doesn't look like the right folder.
Two folders to contend with right now, guys, and that's
B. We have to go to
B. Okay, that's actually in the PDF. Oh, there we go.
Before we tested the PDF, it looked fine. But it doesn't move forward. Can I go to full screen mode? But before it worked perfectly fine.
Was it on a PowerPoint or PDF before?
It was PDF as well. As a water break. Can you go to full screen mode? Then it should work. Now it works.
Okay, I think everything's working. We're ready to go. We have Joachim Bestenleiner from the University of Sheffield be telling us how to find stellar wind properties of massive stars with these spectra. So, Joachim, when you're ready.
Yeah, thanks a lot to the scientific organization committee to give me the opportunity to talk about deriving stellar parameters and wind parameters from the not only Ulysses but also from the X-shooter data. And the big question why we want to do this also. So first we want to know the stellar wind physics of massive stars and how they depend on metallicity, because it's very important if you want to extrapolate it to the high redshift universum, where also the metallicity is lower and we also have different feedback mechanisms and so on. And it's very dependent on the mass rate as well as on the temperature of the star and how the star is evolving as well. Then also we want to know the stellar evolution and population synthesis model. You have to provide massless description, which scales not only for Milky Way metallicity, also down to half solar and 20% solar and even lower, 1/10 solar and so on. And depending what you have here, how much the star is also losing the Anguma momentum. Then it also impacts the rotation, which then also impacts your chemical mixing as well. So you also want to know how the star is overshooting, is it mass dependent, how it's connected to rotation and other parameters and so on. And this is another big question what we want to answer with the Ulysses data on X-shoot data. And this is actually very important if you look at the low metallicity universe, where you have these compact marginal events from gravitational waves, as well as gamma ray bursts, which has a metallicity upper limit, it's predicted. But also for the superluminous supernova, which is extreme, or the most violent events in the universe happened. But also, if you look on the evolutionary timescale of galaxies and so on, you want to understand the radiative feedback, mechanical feedback, also the chemical evolution of galaxies, which also is always connected, how massive stars evolving and how they produce metals and the metal yield. And to really understand all these things, what we want to know or what we need are the stellar parameters of massive stars. So just to get with the current picture, what we knew around 4 years ago, this is now a census of all massive stars, more masses than 15 solar masses in the Tarantula Nebula in the Large Magellanic Cloud. So what Jörg told you in the morning, that here the most massive stars actually don't evolve vertically, what is predicted by those evolutionary models, they evolve horizontally. And what they can, maybe I should. Okay, then we continue. So this is now that you have the well-populated region around the main sequence, and you have here blue supergiant, but not very luminous, what is predicted from evolutionary model as well as from population synthesis model. So in general, I would say the evolutionary models and the population synthesis models kind of agree, but the observation not at all. Also, you don't predict much red supergiants, which are more luminous of 10 to 5.5, which is, for example, Ben Davis 2018. But also you have a much lower number of Wolf-Rayet stars observed than actually predicted, which has also a direct impact on the feedback, mechanical as well as radiative feedback. But also if stars don't evolve too much to the red and they're more continuous around the main sequence, they're usually hotter, which also has an impact on the ionization flux as well. So to really understand what's going on the most massive star, how the masses rate impacts the evolution of the most massive stars, but for the lower mass stars around this region, massless as well as rotational mixing or core shooting is an important part as well. And this is why you have to connect wind as well as stellar structure together to understand what's going on or to improve our understanding of massive stars, to really calibrate population synthesis model as well as evolution models where the interpretation of unresolved population in the universe are based on. So what you basically need is a whole list of stellar parameters. So you want effective temperature, surface gravity, micro and macro turbulence, as well as your protected rotation velocity, which you have to somehow disentangle to understand what's going on. And also you want the bolonomic luminosity, and for that you also need a reddening law as well as extinction. But also for the chemical evolution, you have to understand you want the helium abundance as well as CNO. But also for the masses rate, you have to get all those wind parameters as well, which already Marsha told as well. So if you now continue to look for the effective temperature, what you want photospheric lines which are close nearby, and you want the ionization balance between ions between helium-2 and helium-1 for the hotter stars, as well as nitrogen-4 and 5. But also for the B stars, you line silicon-3 and silicon-4. You can see here silicon-2 line as well as silicon-3, and for the hot stars, you have your nitrogen-4 as well as nitrogen-5, and also a bit of nitrogen-3. But also you have helium-2 and helium-1, which is not present for the early O stars, but you have helium-1 only for the B stars. So you need also some metal lines as well. And the surface gravity is based on your pressure broadening of the Balmer lines. But if you go into UV, which is dominated by the wind, your scale height is actually defined by the velocity law. This is why you can't determine log G on wind parameters. So this is why you need a pressure broadening scale height, which is defined near the photosphere. But this is why I need the optical as well, and not only the UV, or vice versa. So if you now go to look into how to determine the luminosity, what you in the optical and near infrared, you determine the reddening law as well, the extinction, which is defined in the optical and near infrared. This connects to this point. But if you want to learn about the dust properties, which, for example, this dip here or this deal, you can also fit additional parameters for the dust property, which is provided by the Gordon reddening law. And PhD student, Thea Kusa, he did a very nice job and has a nice fitting routine by using the UV detail as well as the optical SED and the photometric points to have a universal fit to not only extinction and reddening law, but also the dust properties. So there's a lot of interesting things what you can learn from those data as well if you did a nice fitting project. So now chemical abundances are a bit more tricky because you kind of need your stellar parameters already fixed. You know your log G effective temperature. You also need all the wind parameters, because some lines which are very strong also depends on wind parameters like X-rays, and also because some lines, the lines are formed at different depths, they're also depending on the microturbulence velocity. So what they usually in the microturbulence for the lower resolution spectrum or in general is usually overlaid by your rotation profile. You can't disentangling it. So what they usually do, you have several lines where you trust the atomic data, and then when both lines get the same results, this is where you fix your microturbulence. So you vary microturbulence until you get a consistent result. But if you now include UV lines, you also depend on wind parameters. You have an additional handle on it. So you try to get a handle on UV plus optical, which depend on different parameters, and so on. So, and then you have, for example, the submitted paper 4, I think is, or paper 6, where I can see the nitrogen abundances over oxygen versus nitrogen over carbon. What you can see now, the two equilibrium lines for CNO and CNN equilibrium. It depends on the CNO process and also how well the stars mixed in to the top. And then you can see the two maximum minima, and then the star should, if it behaves well, should lie between those two lines. So now, if you want to understand the wind physics, then you go, of course, to the UV, and then you have here the nice carbon lines. You have silicon-4 and nitrogen-5, but also you have some other ionization stages as well. And depending how the line is formed and how the line shape is, you get idea of the terminal velocity, and also the masses rate and wind homogeneity. And the red is the observation, and black is the model. So it's a nice fit, and this is what you want to really understand everything. Now, Callum, he did a nice study already, which is now finally allowed to publish, which is good. And he actually fitted the resonance line. On the traditional ways, usually if you have a black absorption, then you just go to the black absorption and you have this, you have the terminal velocity. But if the line is not saturated, you have to use the Sobolev with exact integration method. Also, what is nice, you can see this gradient over here. This gives you a handle on the wind turbulence velocity, it can be several hundred kilometers per second. And what you get then out, if you combine with literature from the Milky Way and also columns, LMC and SMC, you have a very nice temperature and velocity dependence, which is more convenient than the traditional VSK velocity. because with this one, you can really easily compute entire grid and using his relation, which is in most cases, also nearly always very consistent what you need. So now if you want to understand the velocity law, you have to look at lines, because lines are formed in different parts of the wind. So depending on the velocity law, you can change where the lines are formed. And when the line, depending where the lines are formed, you also change the line profile. Because the density, also the velocity of the wind defines the wind density. And the velocity law and the stellar atmosphere code is usually parameterized by the beta type velocity law, because the momentum equation is non-linear. But you can also do hydrodynamic consistent model, but then you have to update the hydrogen structure, radiation field, and your non-LT departure coefficient, and so on, which is very time computational expensive, and it's not feasible if you want to analyze hundreds of stars. This maybe you can do for 1 or 2, but not more. So also, when you look at looking at the same spectral type of 2 stars, you can see that the lines are much weaker if you go to lower metallicity. You have already clear dependence on the metallicity for the masses rate, but just looking on the wind and emission feature, what they have. So, and also to get a handle on the clumping, what you want to compare is you compare resonance lines, which are scaled with the density, and also have recombination, which are density square. So if you use a volume filling factor, so you compress to 1/10 of the volume, then your line density will increase by the square root of 10 for a recombination line, while resonance lines have only scaled with the masses rate. So this you already have a handle on how your density structure and also your clumping factor will look like. But this is only works for the optically thin clumps. Now for the optically thick clumps, John Sundquist developed a parameterization for 1D models, which also includes now the interclump density, as well as your density of clumps, your velocity dispersion of clumps, as well as your intrinsic clumps movement or wiggling around. And this is nicely described in Sarah's Brunst et al. Paper. And this now considers optically thick clumps as well. And optically thick clumps are actually observed in the UV spectrum. And then PhD student, Timothy Parson, he did that you can see now here the narrow absorption components, which are actually located at the blue edge of the star. So you can see the overall trend. This is what your general velocity field is, but you also can see the optical thick clumps, which occurs in little absorption features there, but you also nicely see on the Ulysses spectra. And they're really variable on time scale of a few days, which is also very nice to see. So now, when you combine all the information what you want, we take now the UV spectrum. We have for example, the sulfur 4 line. You can go then from the fuse range, you go to the Ulysses spectrum, have your silicon 4, carbon 4 to your optical spectrum. And what you can see, for example, now the high ionization like nitrogen 5 or oxygen 6 are not predicted. So this is now an indication where you have to include X-ray in your models as well. But I would consider it more like a cosmetic thing, because it doesn't really change the masses rate. It only makes the fit pretty. So, but you can still learn about the general how work temperature or how much X-ray to require into it, which is also a nice thing. And then, Alcuso also doing a lot of modeling in this. Also, you can see now here nicely the iron forest as well, with all the little tiny lines. So if you now zoom in, if you're, for example, in the optical, you have basically one emission line or one diagnostic for masses rate, and you can fit a lot to it. You can highly fine-tune the spectrum. Here you have the Elikon scattering rings. Here you have the absorption where you can calibrate the beta law. But if you not compare to the UV, the UV may look completely different. So what you have to do, you have to find a compromise between optical and UV data for all the lines to have an overall good fit to everything. But also if you now look to the sulfur 4 lines, it doesn't really fit. It's maybe because we have only the optical thin clumping includes, you need an optical thick clumping as well. So now, to continue now how to analyze stars, usually if you traditional or still today use the by eye analysis, and then the uncertainty are estimated and usually underestimated. And there are differences. And in our collaboration, we use the chi-square minimization is either the genetic algorithm. Also, you have a grid base, what I'm using. But the problem is if you use atmospheres and if you use the chi-square minimization, sometimes you end up with a massive cloud because the models are not really representative of the real observation. And at the end, you still need human verification. So because models are imperfect, due to missing physics, atomic data, or 1D model, on Sundquist we talk about 3D models, which are more sophisticated. But also, the model uncertainty what you have should be also budgeted in. And if you use the entire spectrum, then you should also close your observational error as well as your response function, which basically matches the synthetic spectra to the observation as well. And to de-analyze the model, you introduce another model error term, which is this one over here. And then the model error is then based on a large sample of stars, and you can read in my paper all the statistics what you want. So what I now did is I took all the available XShoot data and analyzed all stars in LMC in less than 10 minutes. So because we are interested in the wind physics, we don't want to mess around along too much on the optical data. We really want to, because the wind physics is more tricky or more challenging to analyze. So I want to do a very quick process. Then I used the fast stellar atmosphere code where I can compute hundreds of thousand models in a few weeks. And I included also more rarely used near-infrared diagnostic at the end. And then what you get from the optical is all those parameters, but not really direct masses rate. You have a wind strength parameters, which is actually merge all the stellar parameters into one parameters, like thermal velocity and quantum factor. And there are different scaling relations you can use. This is also used for computing large grid of stellar atmosphere models, because then you can just fix the luminosity and don't need to vary luminosity as well. And then therefore, absorption lines dominated spectra use the wind strength parameter Q because it's the integrated optical depth is preserved over the resonance area. And if you, for emission line stars, you usually want the equivalent width preserved, and then you use this scaling relation. Both scaling relations are identical except of the exponent of the thermal velocity, which is 3/2, and here it's proportional. But if your thermal velocity is similar, then it usually doesn't have any effect on it. So, and then what you get out is you get an 40 effective temperature helium band as well as log Q. And for visualization purpose, I only show the 3D one because this is what you can imagine in it. And then you can see here the temperature cloud is over. It's over here, but you also have here, if you close the Ring limit, kind of degeneracy where your effective gravity is constant, and then you can have similar. You can have similar ionization balance, but with different temperature and log G combination. And then in the log Q effective temperature area, you have here this blob then going up here, and the same for the surface gravity as well as in the log Q. So this is now with a star which is a decent wind, which has some wind features in the optical. But if you have a very low wind density, like around 13 or lower, then you can basically see it's unconstrained. Anything is basically possible what you have here. And this is why you need the UV actually to go to lower wind strength parameters. So, and this is now, for example, the fit of those two stars. On top, you have this AZD fit. Now I'm not fitting the glass dust properties as well. You have here the B star, where you have actually a wind strength of 3.5, and everything is based on absorption. And for this star, you have a bit H alpha and helium-24686. You have some idea on the masses rate. But for this one, you have no idea. It can be 13.5, it can also 15.5. So you have basically no handle. But on the other side, because it's a grid-based one, sometimes because you have the gridding of your nitrogen abundances, you overestimate the temperature a bit. But it's now resolved in the next generation of grids I have computed. So now if you compare now tailored analysis by eye versus grid, then you can see it's pretty consistent what my pipelines provide as well as what our PhD student is doing, except for the lower temperature and where we have problem with the grid edge and also with convergency of the model. So it's not this why you have this offset. Otherwise, effective temperature and log G are very consistent. So you can also measure the radial velocity by just using a cross correlation function. Also, when you analyze the cross correlation function, you also have an idea of the binarity, because sometimes you have a double peak. It's often merged together, but you can, when you use the first, second, and third derivative, you also can still recover the radial velocity of the interval components. And this is pretty condition what you expect from the SMC as well as LMC. Now, rotation rate is usually to improve the fit, but you can also see that the rotation rate peaks within 1800, which is common, which is common for the most massive stars as well, or for the massive stars. And this is pretty similar for the LMC as well for the SMC. Now, this is now the first complete HR diagram of the 200 stars. And you can see between LMC and SMC, you have this nicely covering all parameter spaces from early O to late B star. This star over here, this one of 2017 Massey's identified WN4/04 stars, but my grid is not going hot enough. This star should be located on this side, but you have another similar solution on the other hill of the star. So this should be more like here rather than here, but it's now via signature as well. So now we look at the massless property. So first of all, what you can see, if you go for massless rate, to derive the massless rate, you need a scaling relation for term velocity, as you used in Kalam's relation. You have to assume then a clumping factor, and you have to set your beta law to it. And then you can get from the wind strength parameter to a true massless rate. And what you can see now here below, massless rate of 10 to minus 6, actually everything is all over the place because it's basically unconstrained on the optical. What you also nicely see now that you have a systematic trend between LMC and SMC. SMC is slightly lower, but also now the tailored analysis stars also usually better increment with the SMC one. So basically the clumping factor, what I'm using is a bit, it's actually larger, maybe 20 or 0.05 rather than 0.1. And what I'm fitting through is now my master's description, which is based using the CAK alpha parameter, and which should be melodicity dependent because you have less strong lines at lower melodicity, so you have a lower alpha, and as you nicely see here as well. And if you go to high adding parameters, also close to the adding limit, then your massless rate just becomes independent of melodicity, and you have just continuum dominates over the massless driving. So even though in metal-free environment, if you're close enough to the adding limit, you should have also optical segments. And then if you do it in a more sophisticated way, which is now with the Kiwi code, with the generic algorithm from Sarah, you can see now, she also included now the R136 stars, and you have slightly different relation, 0.53 or 2.5. But this is because the STIS vector are lower resolution, what she used, also much lower signal to noise. So the massless rate is not really constrained here. But overall, you have a good agreement with this massless description as well. And if you compare both massless rate, this is slightly lower as well. So the massless rate is maybe 0.1, 0.2 dex lower, what you just assume when you assume some average clumping factor and so on. Now, also interesting what now Frank Bex is doing. He now compared the Milky Way wind momentum luminosity relation from the Milky Way LMC as well as SMC. And now the slope of this wind momentum luminosity relation is basically 1 over alpha. So again, see you have here larger alpha for the Milky Way and then lower alphas for the SMC, which is pretty consistent to the previous plot as well. And you have a different slopes depending on metallicity as well. So a simple mass throughout proportional to Z scaling relation wouldn't work because you have different slopes over here. So it's not a constant offset, it's just different slope as well. And then I would like to refer to a few more talks which are coming up in this afternoon about the massless rate around the stability charm, how it's changing, but also of a general benchmarking quantitative spectroscopy analysis of material on Wednesday morning. And then just to summarize, so we really need a UV spectrum to study the stellar wind physics, but we still need the optical spectrum to anchor our stellar models there. And then, and Callum's results actually helps also to compute a large amount of stellar atmosphere model, because the terminal velocity is well defined and it's pretty good and consistent with your observation as well. And there are already quite a lot of paper on preparation, also in detail on clumping factor as well as on chemical abundances. And then what I now am doing, I now anchored my effective temperature, and I'm continuing over the last couple of months to also analyze in detail the UV spectrum as well. And then maybe in 3 to 4 or 6 months, you have a homogeneous analysis for optical as well as UV of all the Ulysses exuded data. And then we have new results, relation, everything else, and then we can put everything in this evolutionary models and everybody will be happy on how we can solve. Probably not. Thank you very much.
Thanks a lot, Joachim. Do we have any questions in the room or online? One up there.
Okay, thanks for the nice talk. I have a quick question about the modeling the escaping spectrum to fit the metal resonance line, because as in your talk you mentioned like to get the escaping spectrum, so using Sobolev approximation. But if the medium is clumpy, the scattering behavior is complicated, so that that approximation is not really working. So in the clumpy medium modeling, also do you use the same approximation to get the escaping spectrum when you compare the resonance line spectrum and simulated spectrum and observation spectrum? For example, carbon 4, nitrogen 5, or oxygen 6.
Do you mean this plot over here?
Yeah.
So
generally in the modeling part.
So what Callum is basically doing in the Sobolev explanation, or maybe Callum, you can answer it, is so he takes kind of a temperature and you have the velocity gradient which dominates your all your small scale physics, and then you fit it through the lines what you have over here. So this is now, it doesn't fit the small tiny features, it fits only the general trend of your wind structure. So it doesn't go into the detail of microclumps or optical thick clumps. So, but you can do this without using a stellar atmosphere code, and this is the advantage of this approach. So it's not something you want to have high detail fitting of clumps in the spectrum itself. And this is what you also can see if you go to Timothy's person, he fitting the overall trend, but he doesn't fit the small scale structure. But it's important to identify what the depth is here, how thick the clumps are to estimate them. So does this answer your question?
Oh, yes, thanks.
Hi, thanks. So your results about the alpha parameter is quite interesting. I mean, CAK is alpha, the line force parameter that's lower in the SMC. It's quite intriguing, I must say. Have you tried to see if this is compatible? Have you tried to calculate it? That's what I'm saying. I mean, this is essentially what you get out from your empirical fits, right? Have you also tried to back calculate it to see if it actually comes out?
As a Joe Pultz in his review 2003, I think it is, he predicted theoretical alphas.
Right.
And they should decrease with decreasing.
Yeah, I know. I mean, but he did it for 1 point anyway.
Yeah, for one example.
Yeah,
but this is now also an effective alpha.
With our new prescription, we can actually calculate them. Also not just as 1 point, but as a radial function. So it would be very interesting to do so and see if we should talk about that.
Yeah, but this is really an effective alpha going from, but the detail one would be interesting, what you get out of it and really compare it.
Can you go to page 9?
It's page 9.
So I'm one of the handful ISM CGM people. I'm going to ask about the teeny absorption lines there. So those are absorption lines by the Milky Way and the NMC, and you see that they are actually non-trivial. They're pretty broad.
Yeah.
So, and I think this is one of the better spectrum. You can separate them pretty well. So my question is, in your modeling of the stellar parameters, how can you account for those or get rid of those so you can get a better estimate of the stellar parameter?
So this is like with neighbor lines. It's the same issue. This is influence results. But in my approach, this goes a bit into model error because it's not included in the model error, but you have a different parameters where you look at the moment of the uncertainties. And this will absorb, this we can put the neighbor lines and also the interstellar lines into it because they're non-stellar. This is why important you have lots of stars to compensate that you know what is non-stellar and what is stellar, so you can disentangle it. So it's a bit more complex, but you have to use a statistical method to actually do this. So it's possible, but it's
Okay.
but it's
So-
always, but
so
it should go into the uncertain because it affects the uncertainty. Yeah.
So you have like priors from other wavelengths that kind of help you to determine what it's going to look like in, say, silicon-4, carbon-4.
Yeah.
Right. I see. Cool. Thank you.
Thanks. Anything we can thank Joachim again? And now we're on to the next speaker, which I believe is Paul Crowther, also from the University of Sheffield online. If we can switch over to Paul. Your slides, Paul.
It may be safer to share the slides from each one out. Someone can press the button.
Sure, Alex is setting that up now.
How's the audio?
Okay, I think we're ready. Oh yeah, 1 second. All right, whenever you're ready. And then do you want us to just click when you want the next slide?
That's what, near the end. So
Okay.
apologies for not being able to. It's just over 5 years since Doug was on the boat. Side of things, I would say there are one for the stars themselves, about stellar media, also yeah. or, galactic populations where you already have up with something on the whole of so of course those hereby spectrum of that is a the bottom we now have an and then fixed in this pass to pull out properties. But this is I would say a challenging thing to do. Next slide please. Because the thing is, when you do the population synthesis, as Klaus, who may be in the room, well aware of, is you have to combine, an assumed initial mass function, some models, either empirical or stellar spectra of the stars at any given point in the evolution of those stars, stick them all together, and I would say hope for the best. Because the challenge is that the evolution models incorporate all sorts of uncertainties in rotation and mixing and mass loss. And most of them tend to not worry about binaries, and massive stars tend to find themselves in amongst close binary environments where they have close binary interactions that complicates the evolution. So trying to come up with a robust population synthesis for an integrated population is really tough. So I'm a simple observer, so I kind of thought, okay, let's see if we can produce an empirical UV template to test these state-of-the-art population synthesis models against. So, next slide. So the target of interest is that central ionizing nebulosity within the Tarantula Nebula. So on the left-hand side, we can see the HST image of the inner region of the Tarantula. The box actually shows a news pointing 2 by 2 arc minutes, 30 by 30 parsec. Of that, so we have from the ground-based data, we have an integrated spectrum of that central ionizing nebulosity, and then the middle panel, which kind of shows where that region sits in terms of PPT diagram. So it's basically that red square, very close to the sort of green P galaxies. So it is, I would say, if it was a separate galaxy, it would be pretty much an extreme emission line galaxy. And the right-hand panel shows on the x-axis it's the size, and on the y-axis it's the star formation rate from H-alpha typically. And so the gray region is basically local star forming regions from Pennicut, and all the different colours are a variety of redshifts, clumps or galaxies in terms of star formation rates per unit area, unit size. And that central region, that red dot, thanks, sits actually quite close to some clumps in high redshift galaxies. So it's quite, I would say, quite a high star formation intensity per unit surface area. Okay, so next slide. So how did I go about producing this empirical UV spectrum? Well, I exploited Elena Savi's photometry in the near UV. And I mapped that onto the far UV using data sets within the Tarantula. There's over 1,000 OB stars in the Tarantula that we have spectral types from a variety of sources, from the NTT, from Chris Evans' VFTS survey, from my own survey of the central cluster, and from the news data set I talked about a moment ago. And so, in terms of trying to put together an integrated UV spectrum for that NGC region, I used basically 3 main sources, and I'll show you an image of that in a moment. First of all, using archival HST data of the individual stars, and then we pulled in the Ulysses dataset from the NMC. So for the bright sources, I basically used spectral type. I was able to pull in an empirical spectrum of that spectral type from Ulysses. And for the really faint stuff, I basically assumed it was like an early B dwarf and used that for the really faint things. So next slide hopefully will make more sense. So this is now showing the central region. The box shows the region of the muse pointing. So if we click on first, we go to an object. There we go. So that's one of the brighter objects, which is the Ulysses target. So we can use that spectrum. If we click again, we get another one. So now a B supergiant from Ulysses. Click again. We get something which is now a really faint thing, and all really faint things tends to be very late early B dwarfs, and so I just said, okay, let's have lots of those things to feed in for the integrated spectrum. And then finally, if we click again, a subset of objects, often bright objects, some of these have been observed in geo programs, and this is one from Formation R or R140A. Okay, if we move on to the next slide. This will show now the integrated UV spectrum of NGC 2070. O stars shown in kind of pink, OB stars shown in pink there, dominate the overall continuum and the carbon 4 line. The B supergiants within that tend to be a major player in terms of silicon 4 line. And then 1640, which Yorick mentioned earlier today, arise from both a combination of classical Wolf-Rayet stars and these very massive 100 solar mass or more main sequence stars. They're shown in the red and the blue. So that's what we can see. So that's the integrated UV spectrum. We now move on to the next slide. Then and also break it down not only in terms of what types of stars are responsible for that integrated spectrum, but also how we can actually compare the whole region compared to a central cluster. That contributes about a quarter of the continuum and it contributes a fair fraction of the 1640 emission as well. Whereas R140A, with this O plus this WC plus WN system, that also contributes quite a lot to the integrated 1640 emission. Okay, so next slide can compare now how that integrated spectrum, it can be reproduced, or maybe not perfectly reproduced, by state-of-the-art models, the Starburst 99 at the bottom, Brizot-Charlot top right, and BPAS top left. And overall, I would say they kind of look similar, but on the details that we might care about, they tend to all have deficiencies, either in not being able to reproduce all the lines at once, often missing 1640. So there's basically missing, I would say, physics within all of these models to some degree, even if the overall appearance is broadly similar. Okay, next slide. So that was basically a paper that we published just last month. But for this meeting, I also thought, okay, what about the entire tarantula? Because that was looking at the central region. But now, what would be the integrated spectrum of the whole tarantula? And so basically anything within 100 parsec of that central cluster, I then said, okay, let's try and produce a cumulative spectrum in the far UV of the entire region. So in white, we see the entire tarantula, and in red, we see the central region that was in the muse pointing. So the overall appearance actually is very similar between the two. If we click again. I've also broken it down by basically on that large region, where's the helium-2 come from? So in the central cluster, it's all from the very massive stars. For the R136, for the NGC region, it's probably 2/3, 1/3 classical Wolf-Rayet stars to very, very massive stars. On the integrated picture, I would say majority is from classical Wolf-Rayet stars, because we have very few very massive main sequence stars in the outer regions of the tarantula. But the overall spectrum is, I would say, very similar across all scales, on parsec to tens of parsec to, in this case, hundreds of parsec across. Okay, so my final slide, I think, is next. There we go. So I would say, in summary, I would say this ability to produce now, thanks to Ulysses, an integrated spectrum of the whole region of the tarantula, a very rich star-forming complex, thanks to Ulysses, allows us to basically do a proper comparison of integrated UV spectrum compared to models. The models tend to be okay-ish. They give ages between 2 and 4 million years. And on the top right, we see the age distribution of individual stars, OB stars within the whole NGC 2070 region. On the lower right, we see that from the central cluster. So overall, the averages are about right, but of course, in reality, you're looking at a range of ages. So what's missing? I would say details of very massive stars and binaries and this complex, star formation history. And so with that, I will finish. Thank you for your attention.
Thanks a lot, Paul. Do we have any questions? One here.
Thank you, Paul. This is Aida. Have you tried comparing your empirical integrated spectrum of NGC 2070 to 3125A1?
Yeah, I mean, as you could probably see from the spectra that I showed, overall it's broadly similar. I would say, of course, you're probably more interested in the 1640, and so I was just looking just earlier in terms of the 1640 strength. So in the central cluster, it's about a 6 angstrom equivalent width, and for the 2070, it's about 5 angstroms equivalent width. Emission, similar 4.5 maximum. Over the whole tarantula region, it's up to, again, about 6 angstroms equivalent width with a slightly narrower 4.5 max. But overall spectrum, actually, it looks a bit like an OFWN star at the central cluster, the NGC region, and the whole tarantula, just because you have some really impressive classical Wolf-Rayet stars on the large scale.
Okay, thank you.
Okay, I think can do one more quick question.
Just to add on, I have, I'll have to speak loud. It's, what? To add a, it's,
Okay. Not sure if you caught all of that, Paul, but
I did, and I just want to thank Sally, because actually I used Sally's HRS spectrum 0136A in my cumulative plot because it had a higher resolution than my STIS data. So I did make use of Sally's central cluster spectrum in my integrated spectrum. Thank you all.
thanks again. And now we're on to the last talk of this session before the break. So this is Olivier Verhama, who will be talking about the bistability jump with the Ulysses spectra and the LMC. So, Olivier.
Is this working?
Go full screen.
I think under views, I guess. View and then settings. Oh, I don't know. Under view, right? Put it full screen. Put it full screen was somewhere under view, right? Yeah. How do we did before with UF? Wasn't it also view on it?
Oh yeah, slideshow. Yeah. Okay.
Okay. Cool. Okay. Hello, everybody. Open. Hearable online as well. I think so. My name is Ullyses. I'm from the KU Leuven, and I'll be talking about empirical mass loss rates across the biostability jump from breed supergiants, and these are specifically LMCB supergiants. And obviously, I'm using Ulysses to get a mass loss rate. So I can talk about this slide a bit, but I feel like there's been a lot of introduction already, very good introduction on why we care about massive stars, why we care about mass loss rate. Quickly want to highlight that these mass loss rates, many times have been said already, they are very important in the evolution of these massive stars, right? And just to kind of show this, these are like two MESA models, very basic MESA models, nothing special going on. The only difference between the two is that we changed the mass loss rate prescription a bit. So we just switched around between the normal one and then reduced it a bit to see how different the stars actually end up. And you see that not only is the end product very different, but the way of actually getting there is also very different. Just trying to highlight again how important this mass loss rate is for these massive stars. Now, I also made this bracket around a certain temperature region. That's because that's the temperature region I'm focusing on. That is because there is something special happening there, and it's the biostability jump. Now, first off, the biostability jump has been noticed or observed as this discontinuity in thermal wind speed over escape speed. And it's first been done in 95. And then later, in 99 and 2001, Vink actually showed that this might also be corresponding to a mass loss rate jump in the opposite direction, so a mass loss jump upwards. And this should work. Ooh, this is tricky. You see the mass loss rate prescription that they come up with in 2001 here. And you see the discontinuity of the biostability jump at around this 25 kilokelvin range quite well. You see that it's like almost an order of magnitude difference for this specific mass and luminosity I'm plotting. More recently, as has been indicated by Vink in his previous talk as well, there is some people like Björklund who ran similar type of investigations, and they did not find this biostability jump anymore. So they just do slightly different things here and there with how they do the models, but the biostability jump kind of just disappeared. Now, the goal of what I'm going to do, what I have been doing, is figuring out if this jump is there or not. And because the difference is so big between having a jump and not having a jump, I actually don't need to get the mass loss rate that good anyway. Like, it would help if it's as good as possible, but it should be a very easy problem to solve because there's such a big difference in between these two models. Now, we also have a third model here, which is the Kichka model, and this also has this jump, but it's not really discontinuity anymore, and it's also a lot less big of a jump. So it's like the biostability bump or something you can say. It's not really jumping anymore. Now, I'm not the first person to do this, because this has been a thing that's been known for a while, right? This is a prescription from 2001. In 2008 and 2021, there were other studies who looked at it, but they only had optical data. And we've heard from Joachim, but also before that we actually need the UV data to get good mass loss rate out. And for that, I have the Ulysses and the XShootU collaboration, for which we have this paper from 2023 by Vink et al., to actually help me with that. This has been talked about a couple times already, how the clumping is actually important in figuring out the mass loss rates. So I just have a very specific example here. So if you only have optical data, as been mentioned as well before, the H-alpha is kind of your main line to look at. It's very mass loss rate sensitive, but it is convoluted with this clumping factor. And that's why they usually say that the H-alpha is dependent on the square root rate of the clumping factor times the mass loss rate. So if you have a certain model, like this one, which has a clumping factor of 40, whatever, just a random number, mass loss rate of this, sure, and you get this clumping factor out, your H-alpha line looks like this. And this is your silicon 4 line in UV. But if you now just change it around a bit, and you have your clumping factor to 1, but you change your mass loss rate accordingly to keep the square root of the clumping factor times the mass loss rate consistent, the actual peak of your H-alpha stays the same. And that's the problem why we need UV.
Now, the line shape itself changes a bit. This is due to other clumping effects. But the peak, which is the important thing for the mass loss rate determination, actually stays somewhat similar. So it becomes very hard to determine what the actual mass loss rate of this object is. And this is why having the extra UV here is actually important, because there the change is much more stark, just due to the fact that we get a different mass loss rate clumping factor. So the UV actually allows to break this degeneracy. That's the idea, because they behave differently on the clumping factor. Your actual degeneracy that you have if you only use H alpha gets taken care of. Now, I've talked about 2 lines and a couple parameters already, which we want to get out, which is temperature and mass loss rate. Now we're talking about this clumping factor. In total, we need to get 18 parameters at once. That's the goal. We want to get 18 parameters out of these UV plus optical data at once, which is a lot. How do we do this? We use FastWin, as has been mentioned before as well, to get our synthetic spectra out. The advantage of that one is that it's very quick. And we use KiwiGA, or KiwiGA, which is a genetic algorithm code, to fit them. Now, how does a GA work? I'm just going to do it very briefly, because it doesn't really matter for the purpose of this talk. But we have a distribution of random models. We look at the best fitting 50%, let's say, and we use those to determine the next generation. And that next generation will fit a little bit better, because it uses the knowledge of the last generation. And then we just continue that on until we're happy. If happy means 70 generations, you stop at 70 generations. If happy means a certain chi-squared value, you stop at a certain chi-squared value. That's kind of the idea behind this. And in the end, you end up with an estimate for these 18 parameters at once, and you end up with some spectral fits. The big advantage of doing it this way is that you actually get pretty consistent ways of getting error margins out. This is something that's way harder to do if you do it by eye fitting, for instance, because then you have to figure out afterwards what your error margins are, or just assume an error margin. So having this consistent error margins out is actually quite useful. This becomes a bit more easier to compare, not only in between your own results, but also other people doing sort of similar methodologies with these GAs. Okay? So then, moving on to my empirical results. And here is just first an HRD of which stars we're actually looking at. You have see here that most of them are within these bistability jump range in temperature, and the luminosity goes from 10 to the 5.6 to 10 to the 4.6-ish in solar luminosities, and most of them are past the main sequence. There's some here that are like sort of in the main sequence, maybe, just to give you a kind of idea of where we are in the HRD at the moment. Okay, then the meat of what we want to talk about, the mass loss rates. So I've plotted here the mass loss rates on the y-axis, with on the x-axis the temperature. And the color here I've added is the gamma E, the classical Eddington factor. Why did I add it? The gamma E scales with luminosity over mass. So it kind of gives you an idea of how hard the star is pushing against your mass loss rate compared to how hard the mass is pulling it back. So it sort of gives you an extra indication of where you would expect this to be. For instance, high gamma E, you would just naturally expect it to have slightly higher mass loss rates, because there's either more luminosity to push it away or lower mass to hold it back. These are also the 3 main values that go into these prescriptions we talked about before. That is temperature, mass, luminosity, and also metallicity. But because we stay in the LMC here, you should have all reasonably same metallicity. Now, what do we see here? We see reasonably low error margins overall, I would say, except for the ones with lower mass loss rates. This has been talked about at this point as well. Just because the features become a lot weaker, it's actually just harder to constrain these well. But in general, I would say there is no discontinuity here to see. Now, this is hard to compare because these don't all have the same mass, they don't all have the same luminosity, so it becomes hard to compare with the actual prescriptions. To make that a bit easier, what I did is I took the prescriptions, so I just grabbed the prescriptions from their papers, added in the mass, luminosity, whatever they need that I got from my fits, and there comes out a mass loss rate. I divide that by my empirical found mass loss rate, and now I can make a plot like this, where I show the one line is where you want to be, meaning your prescriptions come across as the same value as your empirical mass loss rate. If you're above the one line, your prescription is slightly overestimating. If you're below it, you're underestimating. That's the goal here. And the gray bars I made here is, again, the region of the bistability. Now, if you go over the 3 prescriptions I talked about in the beginning, first the Vink prescription, you see that it actually does really well up until this 20,000 Kelvin point, at which point the bistability jump occurs in the prescription, and you see that it's overestimating by about a factor of 40 on average. Now, the Björklund rates do a consistent underestimation, so they are on average, up until the 15 kilokelvin mark, under predict by about a factor 2. And the reason they start to drop off here is probably partially due to the fact that this is an interpolation from the models. The actual prescription Björklund made never actually ran models cooler than 15 kilokelvin, so it's probably partially to do with it, but this is how it looks if you compare, right? They're underestimating and then they drop off massively. And you have the Kritichka prediction prescription, which I showed in the beginning as well, and that one seems to do reasonably well over the entire temperature range, but it sort of S's around the 1 range, meaning that maybe there's some behavior there that's not exactly present in the empirical evolution over temperature, but the error margins are too big here to actually figure out if this bump, this bistability bump, is real or not. We just get too high error margins here and not enough data points maybe in the cooler end to confirm if this bump, this Kritichka bump is present or not. Okay, cool. Then down. Okay. I want to briefly talk about clumping factors, and not the clumping factors I showed before, which tells you how dense the clumps are compared to the average. But I want to talk about the interclump density, which tells you how dense the interclump region is compared to the average. So, as talked about before as well, we actually assume usually, or like previously, people always assumed that this was very low or either void. So in a lot of the models, that's kind of the assumption that went into it. In FastWind, we actually have the option to add an interclump density. We actually also thought in the beginning that would always be very low, but it's there, so we fitted it. And it turns out that on average, we actually get a pretty high interclump density out. On average, 40%, the interclump density is 40% of the mean density, which means 40% of the wind mass is in the interclump, which is definitely not void, right? There's definitely something there. And this is on average, meaning that some of them are a lot lower than 40%, but some of them are a lot higher as well. And it becomes very hard to ignore this difference. And this kind of gives an indication into some of the modeling we might need to look into in the future to improve our understanding of these winds. Definitely in 1D, because in 3D, this kind of takes care of itself. To give an example of why this is important to keep track of this interclump density if you're comparing models. In this specific star, it doesn't really matter which star it is, but we got a best fit clumping factor out of 8 and an interclump density of 0.82. Now, traditionally, your clump overdensity is just equal to your clumping factor. If you have an interclump density, that's no longer true. I referred to this paper, but I think there's another paper where it's mentioned as well, to see the full expression of how to calculate it, but also the volume filling factor, which normally is just 1 over the clumping factor, also no longer true if you have an interclump density. So the volume filling factor you get out here is 0.046, and the clumping overdensity is 40. Now, if you would take a model that doesn't have interclump density, and you just look at the paper and see clumping factor 8, I'm going to make a similar model, enter in a model with clumping factor 8. You don't have an interclump density, right? Your volume filling factor is now 0.125, which is 3 times higher, and your clump overdensity is only 8, which is 5 times lower, which means you're actually making a completely different wind than what you thought you were trying to mimic. So this is important to keep track of if you're comparing different models, ones that have and ones that don't have interclump density, if the interclump density is no longer very close or equal to 0. And then, in conclusion, I think in my sample I've looked at here, I don't see any indication of an order of magnitude jump as it is implemented in codes like Mesa at the moment. What this effect exactly will be in evolution, there will be definitely. The exact effects need to be a bit studied more, like we need to run some models to actually know exactly what's going to happen, but it's going to have major effects, I think. And the interclump density seems to be more important than we thought in the beginning, so it might be worth looking into that deeper for future modeling efforts, definitely in 1D codes. Thank you for listening.
Thanks, Olivier. Do we have any questions in the room? Yep.
I was just curious about what's the source of the clumps in these winds, and how do the clumping and interclumps change as the wind evolves, and how is that accounted for in any of these models?
So the source of the clumps is a hot topic, I think. You could look into this line shadowing that causes some instabilities and then clumps, but there's also people that say it should form deeper into the wind. So where it exactly forms is open for discussion. How we implement it is we start at a certain velocity and then we linearly increase it up until we get to the actual value. You can change it in FastWind. It's apparently very easy. I haven't done it. But yeah, this is how we implement it in the code. How it actually happens, open for debate, but probably deeper in, I would say. My guess.
Thanks.
Do you have any other questions? Yep.
I was wondering how you picked your targets. Pardon my ignorance, I'm an ISM person. I'm learning about all of this. In this analysis, I mean, I would think in the Ulysses data there are many more, so I was just wondering.
So I looked at specifically all the B supergiants in the LMC, for which at the time I had both the XShoot U complete normalization present, which there now are more, like they were recently released. I need to do those still. They will be added. I think there's about 8 more that need to be added. And then I did actually basically all the B supergiants that were present at the time in Ulysses, minus some of the ones where I have worries. Weird radial velocities, stuff like that, I just left out. So there aren't actually that many more. I think there are 8 missing from the full Ulysses sample in the B supergiants, except if I made a mistake somewhere and missed some. But I think I got them all. If I used the search form correctly, I think I have them.
Yep, should give you the right answer. Yeah, but if you did this a while ago, indeed, that would explain it.
All right. Nothing on that. Okay, so we can thank Olivier again. And apologies, we ran over a little bit with technical difficulties, but I think we're finished now. We're back in, what, 20 minutes? Yeah, 1:45. So go for coffee and see the posters. Thanks.